Today we're going to, I'm going to do one more example on polynomial functions. I've got one more that I'm going to work all the way through. I feel like that would be a good way to finish that, is on one more video, one more lecture, just go through the whole process of talking about some things with polynomial functions. That'll give us a good chance to review all that. And then the rest of class today, rest of the lecture today, we're going to talk about rational functions and graphing rational functions and the kind of the unique things about rational functions that we need to talk about. Exam 2 material stops with rational functions. So we will go on and talk about combining functions and function composition on Wednesday. We're headed towards exponential and logarithm functions. And so that's what we're going to begin that process on Wednesday. But that material will not be on this test and on exam 2, and that will come up. That will be the material that starts exam 3. I have posted the exam 2 review on your Google page. So that's a big deal, and so start. Go to that review. Get that out and start working through the problems on there. This review is different than the first one in that there's no problems out of the textbook. Out of this review, these are all problems that I've made up, and all of the solutions. I've actually posted this as 2 files. The first file is just the review itself, and the second file is the review with all the solutions, and problems are either worked out or there's answers to the problems provided. So there's a lot of questions on that review. It's longer than the exam's going to be, but that's a good review to look at for the test. The exam 2 testing window opens next Thursday, October 26th, not this Thursday, but the following Thursday. And I will be on campus for office hours next Tuesday and Wednesday, October 24th and 25th. So I do have online office hours this week. Next week I'll be on campus on Tuesday and Wednesday before the exam. So try to take advantage of those office hours if you can. That would be awesome if you could do that. And so, online that's another highlight I should highlight down here. And obviously, I have online office hours this week. I will be sending out a weekly update through the WebAssign probably later this morning. So I'll be reiterating a lot of the stuff that I've just talked about here. So, all right. So let's move on and talk about polynomial functions. Let's look at one last example. This is the problem right here. F of x is 3x to the 5th plus 8x to the 4th minus x cubed minus 8x squared minus 4x minus 16. I've already provided the graph for this particular function, and remember what I want you to do. What we've talked about doing is actually sketching the graph on a calculator or a graphing app so that you can tell some things about the graph and the zeros for the function from the graph. This is going to be helpful, and so it's something I really feel like is part of the process that I'm presenting to you for sketching or for attacking a polynomial function. All right, so you've got this polynomial function. We've got this graph. We want to write down a bunch of information about this that we've talked about many times in lecture now. The degree of this function is 5. The leading coefficient, the coefficient of the third degree term, is positive 3. Because this is an odd degree function, and a positive leading coefficient, we know that the end behavior looks like the cube function, and so the end behavior would be a function that's falling as you move to the left and rising as you move to the right. It looks like the cube function. And in symbols, you could say certainly that as x goes to positive infinity, that's to the right, that y goes to positive infinity, and as x goes to negative infinity, as you go to the left, y is falling, and so y goes to negative infinity. Remember, this is to the right here, and this is to the left right here. All right, and now from this, from here, after getting these couple, and by the way, notice on the graph, that certainly agrees with the graph, in that the graph is falling as you go to the left and rising as you go to the right, also like that. So always take the graph that you've sketched on your calculator and make sure that it agrees with the algebra that you're writing down on paper. All right, the next thing we're going to do is we're going to write down the list of possible rational zeros. Remember, these are just possible rational zeros, and we use the rational zero theorem to do that. And so what we do is we write down factors of the constant, which in this case is 16. It's technically negative 16. So those factors are plus or minus 1, 2, 4, 8, and 16. And then the factors of the leading coefficient, which in this case is just plus or minus 1 and 3. So we take all the factors of 16 and we divide them by all the factors of 3. And so our list looks like this. It's all of those factors of 16 divided by 1. And so it's 1, 2, 4, 8, and 16. And then all of those factors divided by 3. And so that would be 1/3, 2/3, 4/3, 8/3, and 16/3. So that's our list of possible rational zeros. All right, and now we write down the zeros and the factors for the polynomial. And so we look at our graph, and this is where we want to use the graph to our advantage. And we see that we've got what looks like an x-intercept here at -2, 0. And so because that looks like an x-intercept, we think -2 is a 0. And because it looks like a parabola, it looks like that -2 looks to be a 0 of multiplicity 2. So from the graph, it appears x equals -2 is a 0 of multiplicity 2, which means that we think it occurs as a 0 twice. And remember, the reason why we think it's 0 of multiplicity 2 is because the graph looks like a parabola right there at -2. So the graph looks like a parabola. Okay, and then so we've got one candidate with 2 zeros there, and then we have this other 0 over here that's between 1 and 2. And so that 0, that's where we go over to our list. And so the other 0, go to the list and see if a number in the list might match this one. And it appears, in this case, that there is a number in the list that looks like it could match with that one because it's between 1 and 2, but it's closer to 1. And 4/3 is in our list, and 4/3 appears to be a good candidate for that list, for that 0. So we think x equals 4/3 might work there. So that's so those are 3 zeros right there that we think we know from the graph. Now this is a degree 5 polynomial, so we actually know it has 5 zeros altogether, so that accounts for 3 of the zeros, and so our suspicion is that the other 2 zeros here might be imaginary because it doesn't appear like they appear anywhere on the graph at all. All right, so we now use the algebra to prove all of these things. So we start off by dividing synthetically by -2 in our polynomial. Write down the coefficients of the polynomial. And we divide synthetically by -2. So we've done this a bunch of times now in lecture. So -2 times 3 is -6. Add, you get 2. -2 times 2 is -4. Add, you get -5. Negative 2 times negative 5 is 10. Add, you get 2. Negative 2 times 2 is negative 4. Add, you get negative 8. Negative 2 times negative 8 is positive 16. Add, you get 0. So yes, we do have a 0. We've proved it. And we have started the factorization for this polynomial. We know that x plus 2 is a factor because negative 2 is a 0. And we have the other factor has got to be a degree 4 factor, right? It's got to be 1 degree less. So this has got to be a degree 4 polynomial. So this is 3x to the 4th plus 2x cubed minus 5x squared plus 2x minus 8. All right, so now we, remember, we think that negative 2 is a 0 of multiplicity 2. And so we divide by negative 2 again into the new polynomial now, not in the original one. A common mistake is to see students try to divide that into the original one, which doesn't give you any new information at all. You've got to go into this 4th degree polynomial. So you bring down the 3. Negative 2 times 3 is negative 6. Add, you get negative 4. Negative 2 times negative 4 is 8. Add, you get 3. Negative 2 times 3 is negative 6. Add, you get negative 4. And negative 2 times negative 4 is 8. Add, and sure enough, you do get 0. So now we do know that negative 2 is a 0 of multiplicity 2. And so what we've done is we've factored the polynomial again. Right? We have x plus 2 as a factor once. Now we have that it's a factor a second time. And our new polynomial is got to be degree 3. It's always one less than the one you're dividing into. And so this new factor over here will be 3x cubed minus 4x squared plus 3x minus 4, like that. And we do have now another possible 0, and that's 4/3. And so now we divide by 4/3. And, you know, I know that it's a fraction, and so the arithmetic you think might be kind of yucky, but this is not going to be bad at all. Divide by 4/3, you bring down the 3. 4/3 times 3 is 4. Put 4 in the next column, add, you get 0. 4/3 times 0, that's easy, that's 0. Add, you get 3. 4/3 times 3 is 4. Add, you get 0. And so, sure enough, 4/3 is a 0. We have proved it now. And so now our factorization looks like this. We've got x plus 2 as a factor twice, so that's x plus 2 squared. 4/3 we've now proved is a 0, so that's x minus 4/3. And then we get this last factor has got to be a degree 2 factor. And that degree 2 factor would then be 3x squared. There'd be no x term because of that 0. And then plus 3. The 3 is a common factor in that last factor. So you have x plus 2 squared times x minus 4/3. You take out a 3 and you're left with x squared plus 1. You will frequently see that 3 used with the x minus 4/3 instead. And if you multiply that out, this is not a big deal if you do this at all, by the way. Well, in fact, I'll do that, but I'm not going to make a big deal about this at all. So this would be 3x minus 4, using the distributive property there and taking the 3 and multiplying it by the x minus 4/3 there at the very bottom. And then you have this x squared plus 1 right here as the last factor. All right, so where are the other two zeros in this problem? Well, the other two zeros are from that x squared plus 4. And let's see, I think I'm going to kind of squeeze this material in. I'll put it down right down here. In this box right in here to separate it from the graph. That x squared plus 1 is where the other two zeros are. So you set that factor equal to 0. And you solve that. And you end up with plus or minus I. When you take the square root of both sides, you get the square root of -1, which is the imaginary number, and you get plus or minus I here. So the zeros for this polynomial end up being, we're filling in our little space over here. We've got x equals -2, multiplicity 2. We have x equals 4/3. And then we also have x equals plus or minus I. And that does account for all 5 zeros. The x-intercepts are easy once you've written the zeros down. The real zeros are the x-intercepts. So you have -2, 0, and 4/3, 0. Finally, the y-intercept is also easy, because the y-intercept is just substitute 0 for x in the original function, and you get 0, -16 for the y-intercept right there. And that certainly agrees with my graph. This is the point 0, -16 right here. Sometimes you can read that from the graph, sometimes you can't. It just depends. Sometimes the y-intercept is a really big number or a big negative number, and so it's hard to find it from the graph just because it might be off of your screen. But remember, you can always just substitute 0 for x in the original function, and you get the constant to be the y-intercept. So, all right, so this kind of goes through all the work, and you know, this includes a lot of different things in a problem. I typically don't give, in most cases, well, I shouldn't say all the time, but you're not going to see a lot of 5th degree polynomials on the test. You might see one where everything works out pretty smoothly, certainly. But all right, so that's our review of polynomial functions. For those of you who are listening live right now, anybody have any questions before I move on?
I'm good.
Okay. Then, so that's our last polynomial function in lecture. And so now we are ready to move on to rational functions. Rational functions in your textbook is in section 5.6 of your textbook. And so what is, first of all, a rational function? And so a rational function is a fraction that happens to be a polynomial in the numerator and a polynomial in the denominator. And so because it's built from polynomials, rational functions do have some things in common with polynomial functions, but a lot of things that are different. First of all, since it's a fraction, we don't want the denominator to be 0, and so these frequently have restrictions on their domains. And we've talked about that before. We've talked about this kind of function. They frequently have restrictions on the domains. Remember that the denominator of a fraction cannot be equal to 0. So, you know, a simple polynomial or simple rational function like this, we know that x minus 3 is equal to 0 when x is 3. And so x in this function cannot be equal to 3. Right? There's a restriction on the domain for this rational function. And so the domain here is going to be from -infinity to 3. I'm not -3, but 3. And then union 3 to infinity. This never happened with polynomial functions. Polynomial functions domains were always all real numbers. But you can see very quickly that rational functions frequently have restrictions on their domains. And so we need to talk about what the impact that it has on the graph of the function. All right, this is another example right here, x minus 5 over x squared minus 2x minus 3. And so if you factor the denominator, x minus 3 times x plus 1, right? In this case, there's 2 factors in the denominator, and so you set each of those factors equal to 0, and you get x equals 3, and you get x equals -1. And so in this function, what do we know? That x cannot be 3, and x cannot be -1. So we have 2 restricted values in the domain. And so the domain on this function is -infinity to -1, union -1 to 3, and then union 3 to infinity, like that. So it's a more complicated domain. One thing that this implies about the graph is that graphs of rational functions frequently have several branches to them. The first graph, since the domain comes in 2 pieces, right, from -infinity to 3 and then 3 to infinity, the graph on this function has two distinct branches to the graph because there's two pieces to the domain. The next one, there's three pieces there, so this graph actually has three branches. Three pieces to the graph, three very distinct pieces that don't connect to each other at all. And so we're going to want to look at what that implies about the graph of the function. All right, so what we're going to do, instead of starting with equations for rational functions, we're going to start with some typical graphs for rational functions and see what kind of information that we can get from the graph and then what I want you to write. And so that after we analyze some graphs, then we will actually look at some equations and see how we can get the graphs from those equations. So I'm going to give you, we'll start off with some typical graphs here and some kinds of information that I would want you to give me from the graph. All right, so let's say that we have a graph, and I'm just going to hand sketch these graphs. Now, and you'll see what these dashed lines are in a minute as we go through this process. But let's say we have a graph that looks like this. This is a very typical rational function in its graph. Might look like this. Now, right away, what you see, so this graph has two branches, and they're kind of separated with these dotted lines. These dotted lines are called asymptotes for the graph. So this vertical line here is called a vertical asymptote. It's called a vertical asymptote. I abbreviate vertical asymptote VA when I write information out about the graph. And that is a vertical line that the graph of a rational function gets close to, but never actually gets to that vertical line. And for rational functions, these are never crossed. Never, never, never crossed. So I'm going to write that here, never crossed, right here. All right, notice there's a horizontal line that also acts as an asymptote for this graph. And so that's called a horizontal asymptote, obviously. And the horizontal asymptote, in some cases, can be crossed. And we will talk about that as we go through some examples. This particular graph does not cross its horizontal asymptote, but sometimes they will cross their asymptote, their horizontal asymptote. Rational functions can also have what we call slant asymptotes, but we are not going to generally cover slant asymptotes in this class. And so do not worry about slant asymptotes at this point. So we're going to worry more about horizontal and vertical asymptotes. Oh yeah, and by the way, horizontal asymptote I do abbreviate HA for horizontal asymptote. All right, so for a graph like this, what I'm going to ask you several questions. Now notice as we get close to the vertical asymptote 2 from the right side of 2 and from the left side of 2. So if you go over to the graph, this is, I'm going to have to try to kind of explain this visually for those of you, because I can't really point to anything here. But as we move towards that asymptote from the left, and as we move towards that asymptote from the right, like that, that's what we want to talk about. So from the left, we say as x approaches 2 from the left, and we put a little minus sign above the 2 where you might write an exponent, and that means we're getting close to 2 from the left side of 2. And from the right, we're going to say as x approaches 2, put a little arrow there, it gets close to 2, and we're going to put a little plus sign there that says that we're approaching it from the right. So here we're approaching, x is approaching 2 from the left, And here x is approaching 2 from the right, like that. And what we're interested in asking at that point is, what is y doing at that point? And so y, that's actually a much easier question than you might think. Y is just controlling how high or low you are on the graph. And so is the graph going up or is the graph going down as you're getting close to the asymptote from that particular direction? That's really all you're asking. So from the left side, the graph's going up, right? It's shooting up the asymptote in the positive direction. And so we say that y is going to infinity, right there. And then from the right, on the right side, as you get close to the asymptote, the graph's going down in the negative direction. And so we say that y is going to negative infinity. Y is going to be a bigger and bigger negative number is what we're saying there. All right, so I will ask those kinds of questions about the asymptotes. And about the vertical asymptotes in this case. So that's the vertical asymptote questions there. We would do the same thing for the horizontal asymptote. But now with the horizontal asymptote, what you're asking for the horizontal asymptote, and I probably need to erase that because I'm going to need to write right there. For the horizontal asymptote, you're looking at what happens to the graph as you're moving off infinitely far in the right direction. So you're going this way, and so that means x is going to infinity, right? Because we're going to the right forever. And what's y doing? And then the same thing as we go to the left. As we go to the left, as you're moving this direction, right? X is going to the left in this case, and so we say left, and we say that x is going to negative infinity as we go in that direction. All right, and what's y doing? Well, y in both cases, if you look at the graph, you've got this asymptote, and this asymptote goes on forever, and what happens? The graph just gets closer and closer to that horizontal asymptote. The horizontal asymptote in this case is at y equals 1. Y equals 1 is the horizontal asymptote, and so we say here that the horizontal asymptote, as x goes to infinity, in other words, as you move off to the right on this graph, y is getting close to 1, and as x goes to negative infinity, as you go to the left, y is also going to 1. And a little hint there, if there is a horizontal asymptote for the graph, that's always going to be the answer to those two questions. It's always going to be whatever the horizontal asymptote is. All right, now one other thing, and I didn't write this down at the beginning, and maybe I should have, but I would ask you in a graph like this to actually tell me what the vertical asymptote is, which in this case is x equals 2. I'd ask you to tell me what the horizontal asymptote is, which in this case would be y equals 1. And I'd ask you to tell me what the x and y intercepts for the graph are. That the x-intercept in this case is at 4, 0, and that the y-intercept is at 0, 2. Like that. All right, so that's a kind of an introductory graph there. Let's and what we're going to do now is look at several graphs. Before we actually go to equations and try to produce the graphs. I'm just going to draw out some graphs here, and then we're going to write down information from this graph. And I will do this. There is a problem on your review like this, and you will have a question on your exams like this, where you have a graph given to you, and then you're asked to write down some information about the graph. Okay, so let's say we have a vertical asymptote located right there. We have a horizontal asymptote located right here. And we have a graph that looks like this. And I'm going to sketch this in green so it looks a little bit different here. Let's say we have a graph that comes up this way. We have one branch sitting right there. And then we have another branch, let's see, another branch sitting down here like this. Okay, and so the first things I would ask you for this graph, I'd ask you to tell me what the vertical asymptote was for the graph, or vertical asymptotes. In this case, there's a vertical line here at x equals -1. That's our vertical asymptote. The horizontal asymptote, there's a horizontal line here at y equals -2. And so there's our horizontal asymptotes at y equals -2. The x-intercept, and there's no reason a rational function has to have an x-intercept, but this one does, and it's at -2, 0. So we have an x-intercept at -2, 0, and then a y-intercept where the graph crosses the y-axis would be at 0, -4. All right, so I'll ask you those things for sure from a graph, and then I'll ask you some questions about the behavior at the asymptotes, right? So I would ask you, it would be kind of like a fill in the blank here. I'd say as x approaches -1 from the left, what does y do? As x approaches -1 from the right, what does y do? So now those two questions pertain to the vertical asymptote and what's happening at the vertical asymptote, right? And we're coming into the vertical asymptote from the left side of the asymptote. So that's this direction. And we're approaching, and this is on the x-axis, and then we're approaching the asymptote from this direction like that. That's from the right. All right, and what's the graph doing on the left side, and what's the graph doing on the right side? On the left side, the graph is going up. The y value is getting larger and larger. And so we say that y is going to infinity right there. And as you approach -1 from the right side, the graph is going down as you're coming from the right side, as you're approaching that asymptote from the right side. The y value is getting to be a bigger and bigger negative number. And so we say that y is going to -infinity like that. All right, so those are the two questions I'd ask about approaching the vertical asymptote. And then the horizontal asymptote, I'd say as x goes to infinity, that means we're going off to the right. And as x goes to -infinity, that means we're going off to the left. And this is like the end of behavior of the graph. And I'd be asking you to fill in the blanks here. What is y doing? Right, as you're going off to the right and off to the left. Infinitely far to the right, infinitely far to the left. But what's the graph doing? In both cases, the graph is coming up towards its horizontal asymptote. And for a rational function, that would in fact always be the case, that that's what's going to happen. And so those answers would be -2 in both cases, right? Those are the questions that relate to the horizontal asymptote. And the answers to those questions will always be the horizontal asymptote. All right? Okay, so there's another graph. Now, like I said, we have several graphs to look at here. So, because we have several things to talk about. Both of those graphs had 2 branches, and so now let's look at a 3-branch rational function. So let's say we have this particular graph, and it has, like I said, it has 3 branches, and so this one's going to be more complicated. So let's say that the graph has a branch like that, has another branch like this, and then finally has a 3rd branch that looks like this one, like this. All right, so this is a very typical, very common looking rational function with 3 branches to it. All right, so the first things I'd be asking you to write down, I'd be asking you to write down the vertical asymptotes. And in this particular graph, there are 2 vertical asymptotes. There's one here at 3 and another vertical asymptote here at -2. So we have 2 of them. X equals 3, x equals -2. Horizontal asymptote. Now at first you might say, oh, the graph doesn't have a horizontal asymptote, but this graph definitely does have a horizontal asymptote, because notice that this graph over to the left is approaching the x-axis, and over to the right, the graph is approaching the x-axis. And so the horizontal asymptote in this problem is, in fact, the x-axis. And so that is the horizontal line y equals 0. Right? When you say the x-axis or you say y equals 0, you're actually saying the same thing. Those are just different names for the same thing. Notice this graph, the horizontal asymptote is crossed. And the horizontal asymptote is crossed, and it is crossed at 2, 0. So I'm just going to write that down, that it's crossed at that point 2, 0. Right here, that's a place where the horizontal asymptote is crossed. Now, I'm not going to go crazy with that kind of idea, but from a graph, it would be nice for you to be able to identify where the horizontal asymptote is crossed. All right, x-intercept for the graph, and the x-intercept happens to be the same thing as where the horizontal asymptote is crossed. That's 2, 0. And then the y-intercept, the graph does have a y-intercept at 0, -1. All right, so now the behavior as you get close to those vertical asymptotes. There's 2 vertical asymptotes here. So I might say, I'd ask you 4 questions. I'd say as x approaches -2 from the left, what does y do? As x approaches -2 from the right, what does y do? As x approaches 3 from the left, what does y do? And then as x approaches 3 from the right, what does y do? Right, all those questions pertain to the vertical asymptotes. All right, and so what happens at -2? What does the graph do? As you're getting close to -2 from the left side of -2, right, you're coming in from the left side here and the right side here. What does the graph do? It's going up on the left. The graph is going up. The y values are getting bigger, right? And so this would be infinity here. And as you're coming in from the right, this is going to be -infinity. And for 3, the behavior is the same. As you're coming in from the left and the right, you're coming in from the left side of 3 and the right side of 3. Graph is doing the same thing on both sides there. And so this one's going to be infinity and -infinity also. Definitely does not have to be like that. It doesn't have to be in opposite directions. It could definitely be in the same direction as well. That definitely happens. All right, and then finally the horizontal asymptotes. As x goes off to the right, what does y do? And as x goes off to the left, what does y do? Right, remember this is to the right, this direction, that's positive infinity, and -infinity, you're talking about what happens as the graph goes off to the left, and in both cases, the y value is getting close to the asymptote, but the asymptote's at 0. And so you say that y is getting closer and closer to 0, and you can see that that would certainly be true on the graph, that the y value is getting closer and closer to 0. Now on the left side, it's above 0, and the right side is below 0, but that doesn't matter at all. It's just that it's getting close to 0 on both sides like that. All right. So let's, I think, yeah, I'm going to have time for one more graph I want to talk about, and then we're going to actually look at some equations and try to produce the graphs from those equations. All right, so this next graph will also be a 3-branch graph. We won't look at anything. You could have any number of branches on a rational function. We will not look at any 4-branch graphs, just mainly 2- and 3-branch graphs. You can have 1-branch graphs also, ones without any vertical asymptotes. But we're just not going to look at any of those graphs here. So let's say we have this graph. Like that. And like that. And then we have the actual graph. Let's see, so the actual graph will say, looks like this. looks like this. That's a different kind of branch right there. And finally, like so. So those are three distinct branches to this particular graph. All right. So first of all, the vertical asymptotes for the graph are at x equals 1 and x equals 4. Right, here's x equals 1, that vertical line. Here's x equals 4, that vertical line. Please always write these as equations because these are vertical lines. So write the equation for the vertical line, which means, so don't just write 1 and 4. Write x equals 1 and x equals 4. The horizontal asymptote, very clearly from the graph, that would be at y equals 2. That's our horizontal asymptote. And it is crossed. The horizontal asymptote is crossed at the point 2, 2. This is the point where the horizontal asymptote's crossed. And I'm going to label it right there. Right, the graph actually crosses through it right there, and so it's crossed at the point 2, 2. All right, the x-intercept for the graph, easy to read. And if I give you a graph, I'm not going to give you something where you have to, estimate or anything. I'll give you a graph that crosses at values that you could read from the graph. And so this x-intercept's at 3, 0, and then the y-intercept is at 0, 3. All right, so now the behavior of the graph at the vertical asymptotes. As x approaches 1 from the left side of 1, and as x approaches 1 from the right side of 1, we're talking about what does y do. And notice in this case, so this is different than the ones we've seen so far, as you're coming in from the left side towards 1, and you're coming in towards the right side towards 1. Well, the graph is going up in both cases, getting close to the asymptote as y is getting larger and larger. So in both cases, y is going to infinity in this case. Both cases are positive infinity. So that's definitely different than what we've seen before. All right, and then the other asymptote, again, we're coming in towards 4 from the left and 4 from the right. And what's the graph doing as you're coming in both of those directions? So as x gets close to 4 from the left side of 4, the graph is going down, and as x is getting close to 4 from the right side of 4, the graph is going up. So the y value on the left side is going to be a bigger and bigger negative number, and so that would be negative infinity. The y value is going to be a bigger and bigger positive number on the right side, so that would be positive infinity on that side. So those are the two vertical asymptotes, and the behavior of the graph on both sides of those asymptotes. Finally, if we move off to the right on our graph, in other words, as x goes to infinity, y is going to the horizontal asymptote. And as x is going to the left, as x is going to negative infinity, again, y is going to the asymptote, so the horizontal asymptote. So in both cases, that would be 2 for the horizontal asymptote. All right, so that's some pretty decent graphs, some good examples of reading graphs and being able to write down information from the graphs. Notice none of the graphs that I give you were slant asymptotes. I'm not going to ask that kind of question. We're not going to look at slant asymptotes, even though rational functions definitely can have slant asymptotes. That's going to be more a pre-cal topic. All right, so now what we're going to do is we're going to move on to talking about equations and being able to write down information about a graph from the equation of the graph. So we're going to start off with some relatively simple rational functions and write down how we can figure out the vertical asymptotes, the horizontal asymptotes, the x-intercepts, the y-intercepts. All right, so for the vertical, so this problem we're going to go through some, a lot of discussion about this problem, and we're going to kind of streamline the process as we go through problems after that. So let's see. The vertical asymptotes. The vertical asymptotes occur where the graph has a restriction in the domain. So the vertical asymptote is where the denominator is equal to 0. And actually, technically, what you have to write also is that where the numerator is not equal to 0. So now what I'm talking about there is if you have a possibility of a place where both the numerator and the denominator are equal to 0 at the same x value, that is not a vertical asymptote. So how do you get a vertical asymptote? It's when both of those things are true, that the denominator at the x value is 0, but the numerator is not 0. The only time you have to worry about this is if you have the same factor in the numerator and the denominator. And we're generally not going to look at problems like that. But that can happen. But we're just generally not going to do that at this point. All right, so we're going to look at where the denominator is equal to 0. So in our problem, this is where x plus 3 is equal to 0. And so that's x equals negative 3. That's our vertical asymptote. And notice that's all that is just a restriction in the domain. And so all you're looking at for the vertical asymptotes generally is that idea of where is the denominator equal to 0. It's actually an easy thing to do. The numerator also cannot be equal to 0 at that same x value. So if negative 3 makes the denominator equal to 0, it certainly does not make the numerator equal to 0. So that's our vertical asymptote for this function. Horizontal asymptotes are somewhat more complicated as far as how to find the horizontal asymptotes. But remember, if you go back through all of these problems, what about the horizontal asymptote? The horizontal asymptote occurred when x is getting big or small. X is going to infinity or negative infinity, right? All of these problems, you were always talking about the horizontal asymptote being where x is going to infinity or negative infinity, right? Every one of these, this is exactly what's going on. This is always the case for horizontal asymptotes. You're talking about what happens as x gets to be a really big number or a really small or a really big negative number. Really big positive number, really big negative number. So that's what you're doing here is you're looking at what happens, what happens as x goes to infinity and negative infinity in the problem. Well, what happens, basically, one way to look at this is the term with the biggest power in it ends up being the dominant term. It's the only terms that matter. So the only terms that matter and when I say matter, I'm going to put quotes around that. But those are the dominant terms. Those control what's happening to the function. The only terms that matter are the terms with the biggest powers. In both the numerator and the denominator. In both the numerator and the denominator. So what that means is as x goes to infinity, here, our function x minus 1 over x plus 3, the only terms that end up mattering here, the terms that control what's happening to this function are the terms with the biggest powers. And that's the two x's in the numerator and the denominator. The term with the biggest power in the numerator is the x. The term with the biggest power in the denominator is the x. And x over x, what do you get there? You get 1, right? Because the x's would cancel out. And so that's where your horizontal asymptote is. By the way, I've got as x is going to infinity. It's the same discussion if x goes to negative infinity. And you get the same horizontal asymptote either way. So our horizontal asymptote in this problem is that y equals 1. And so that's what we're looking at here, is we're looking at the dominant terms, the terms that matter, and for the horizontal asymptote. And so you're looking at those terms, and those terms control what the horizontal asymptote is. And you'll see different problems as we go through this and how that works out, okay? So as you see more examples, that will become clearer, hopefully. All right, so now what we're doing is we're trying to find all this information out. So here's the vertical asymptotes. What do you do with the vertical asymptotes? You look at where the denominator is 0 and the numerator is not 0. Here's the horizontal asymptotes. What are you going to do? You're going to look at the terms with the biggest powers. Those are what control the fraction as x gets large. And so those are the ones that matter. You're going to look at the terms with the biggest powers, and in both the numerator and the denominator. And that's going to help you find the horizontal asymptote. All right, and then the other information we've got to look at are the x-intercepts. And the x-intercepts end up being where the numerator is equal to 0. Because you're trying to make the fraction equal to 0. And how does a fraction get equal to 0? It's in the numerator is 0, not the denominator, but the numerator. So you just set the numerator equal to 0. So that's easy. Just set the numerator equal to 0. And finally, the y-intercept is simply you set x equals 0, solve for y. All right, so x-intercept, let's highlight some things there. The x-intercept, what do? You set the numerator equal to 0. The y-intercept, you set x equals 0 in the equation, and then you solve for y. All right, so that's how we find all the information that we want to look at for these functions. The vertical and horizontal asymptotes, the x-intercepts, and the y-intercepts. That's the stuff we're going to be most interested in for rational functions. All right. So we're going to look at some more examples. So we have f of x is 2x plus 1 over x minus 5. Right? So using the information that we just talked about, the vertical asymptotes, what do? We set the denominator equal to 0. And when we set the denominator equal to 0, we get x equals 5. And so that's our vertical asymptote, is x equals 5. The horizontal asymptote. What do we do to find the horizontal asymptote? Well, we look at what happens as x goes to infinity. So in this problem, as x goes to infinity, our function, 2x plus 1 over x minus 5, we just look at the dominant terms in the numerator and the denominator. The term with the dominant term, remember, is always just the term with the x power that's the biggest exponent. In this case, those are still just the x terms. And so you keep those terms and you throw everything else away because everything else doesn't matter as x gets large. And so this fraction would approach 2x over x. And that approaches 2 because the x's cancel. And so there's our horizontal asymptotes at y equals 2. The x-intercept. The x-intercept, remember, we set the numerator equal to 0. And when you set the numerator equal to 0, you get 2x plus 1 equals 0. You get 2x equals negative 1. X is negative 1/2. There's our x-intercepts at negative 1/2, 0. And then the y-intercept, finally, we take our function and we, which is f of x equals 2x plus 1 over x minus 5. So that's y equals 2x plus 1 over x minus 5. And we substitute 0 for x. And so when you substitute 0 for x, you get y equals 2 times 0 plus 1 over 0 minus 5, you get negative 1/5. And so our y-intercepts at 0, negative 1/5, like that. All right, because, and now we're going to sketch the graph. We're going to make a rough sketch of this graph without technology at this point. See if we can piece together a rough sketch of the graph. Because there was one vertical asymptote for this graph, the graph has 2 branches. 2 pieces to this graph because it has one vertical asymptote. All right, so we go ahead and draw in the asymptotes. There's an asymptote at 5, 1, 2, 3, 4, 5, right here. And there is a horizontal asymptote at y equals 2, right here. Right, so those are our asymptotes. And now we got to decide where these branches fit in. We know there's an x-intercept at negative 1/2, 0, so there's an x-intercept way over here at negative 1/2, 0. And there's a y-intercept at 0, negative 1/5, which is like right in here. So the intercepts are really close together. And that would give you a pretty good idea where this branch might be sitting, right? If you got branches on each side of the asymptote, of the vertical asymptote. But what you might do is you might plot a few points, a few key points. So off to the side here, let's see, I'm going to do this in a different color. Let's pick x equals negative 2. So that means you're looking at f of negative 2 in the function. And f of negative 2 would be 2 times negative 2 plus 1 over negative 2 minus 5. And so that would be negative 3 over negative 7, or 3/7. So at negative 2, you get 3/7, which is maybe like right about in here. Let's pick x equals positive 3. And so you have f of 3 to be 2 times 3 plus 1 over 3 minus 5. So you get 6 plus 1, or 7, over negative 2. You get negative 3.5. So at x equals 3, you're at 3.5 about, or not about, exactly 3.5. So that would be down here. And so those points are certainly giving you a good idea that this branch between these two asymptotes is located kind of like this, right? And is approaching the asymptote. Erase a little bit of that there. Approaching the horizontal asymptote from underneath the asymptote, and approaching x equals 5 with the y value getting to be a larger negative number. And then the branch on the other side, if you're unclear where that branch might be sitting, you continue to pick some x values here. So you might pick an x value at 6. That would be a good one. Or at 8, things like that. Those would all be good x values to pick right here. So if x is equal to 6, you have f of 6 is what we're looking at here. That's 2 times 6 plus 1 over 6 minus 5. And you get 13 over 1, or 13. So at 6, you're way up at 13, which starts giving you a good idea what's going to happen. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Way the heck up here is the point 6, 13. Like that, right? You know, and this asymptote goes up through my problem here, but it goes up forever in this direction. And so that gives you a good idea what the graph is doing. So your suspicion would be that at 8, the graph is coming down and should be a smaller value here. So f of 8, you have 2 times 8 plus 1 over 8 minus 5. And so you get 17 over 3, which is like 5 2/3. So 1, 2, 3, 4, 5 2/3, like right here in the middle of where I was finding the y-intercept. All right, and you could keep on looking at values like that if you were worried about that. So like you could go way out here to 10. At x equals 10, you've got f of 10 is 2 times 10 plus 1 over 10 minus 5. And so you get 21 over 5, and that's 4 1/5. 1, 2, 3, 4, 4 1/5, like right here. And so you're getting a good idea that this other branch for the graph is sitting up above the asymptote, is coming like this. And I'm just drawing pieces of it through the problem, and it's coming in like that. And so that's our other. So this graph's pretty spread out. The numbers are pretty big. Not going to typically look at problems like that where the numbers are all that big. All right, let's look at another example. So we I just want to kind of start working our way through different possibilities here. So here we have f of x is equal to, let's say we have 2 minus x over 3x minus 3x plus 2, we'll say. Okay. All right, so the vertical asymptote for this graph. So the vertical asymptote is where the denominator is equal to 0 and the numerator is not 0, remember. So where the denominator is equal to 0, and so that would be 3x plus 2 equals 0, 3x equals negative 2, x is negative 2/3. So we have a vertical asymptote at the vertical line, x equals negative 2/3. The horizontal asymptote, we're looking at the terms with the biggest powers, right? As x goes to infinity, what's happening here? Our function 2 minus x over 3x plus 2 is going to approach, and we take the negative x, the x term in the numerator, and the 3x term in the denominator. It's going to approach negative x over 3x. The x's cancel, and you get x equals negative 1/3. And so there's a horizontal asymptote at y equals negative 1/3. All right, the x-intercept. Remember, the x-intercept is where the numerator is equal to 0. So the numerator is equal to 0. And so the numerator is equal to 0 at 2 minus x equals 0, or x is equal to 2. And so there's an x-intercept at 2, 0. And then the y-intercept, we go ahead and set x equals 0 in our equation. And so you get y equals 2 minus 0 over 3 times 0 plus 2. And so you get 1, right? 2 over 2, which is 1. So we have a y-intercept at 0, 1. All right, and then let's see what we can piece together on this graph. And you know, if we want to plot some points in some key places, we can do that to help us with where the branches are located in this graph. Now, because the intercepts, or I'm sorry, the asymptotes are somewhat small on this one, let's see. I think maybe I want to change the scale a little bit. So let's say that that's 1 and negative 1 and 1 and negative 1 like that. We'll change the scale a little bit so we can see these asymptotes. So we have a vertical asymptote at negative 2/3. So there's a vertical asymptote right there at x equals negative 2/3. We have a horizontal asymptote at y equals negative 1/3. So here's my y-intercept, or y-asymptote at y equals negative 1/3. We have a x-intercept at 2, 0. So let's see, there's an x-intercept sitting over here at 2, 0, which would be right here. And we have a y-intercept at 0, 1, which is right here. And so those two intercepts certainly start giving you the idea that there should be a branch to this graph sitting over here. Right, passes through these two intercepts and kind of looks like this. Right, if you were unsure about that, you could plot a point like x equals 1 would be a great point. You could pick x equals 3 or 4 just to show that the asymptote is going to be at negative 1/3 right there, if you wanted to. On the other side of the graph, if you're unclear where the other branch is going to be, again, you might plot some points. And so, for example, on the other side, it might be advantageous to pick negative 1 and negative 2 and see where the graph is at negative 1 and negative 2. So when x is at negative 1, you're looking at f of negative 1, which is 2 minus negative 1 over 3 times negative 1 plus 2. So you end up with 3 over negative 1, or negative 3. Just a little bit off of our graph, a little bit off the screen. But it does give us a negative value there, so that tells us some information there. X equals negative 2. We have f of negative 2 is 2, whoops, 2 minus negative 2 over 3 times negative 2 plus 2. And so you get 4 over negative 4, or negative 1. And so negative 2, the graph's up here at negative 1, which would be like right about in there. And you had a big value way down off the screen down there. And so our branch over here certainly appears to be sitting down here like this. Right, and obviously, let me put that in the same color as the other branch. You could use your calculator to get a better idea about those branches like that. All right, so let's finish this look at rational functions here with a graph that's a two-branch graph. So let's say we have f of x is equal to x minus 1 over x squared minus 9. All right? So there's some different things that are going to happen on this problem. Now, one thing you'll want to do is if there's any factoring, you'll want to do that. So in the denominator factors x plus 3 times x minus 3. All right, so the vertical asymptotes, where do they happen? It's where the numerator is 0. Numerator is equal to 0. Oh, wow, the numerator is equal to 0 would be nice if I said it right? It's where the denominator is equal to 0. That's better. So where the denominator is equal to 0, and so you'd have x plus 3 times x minus 3 equals 0. And so you have two factors here, and you end up with negative 3 and 3. And so those are our vertical asymptotes at negative 3 and at 3. Two vertical asymptotes in this problem. Horizontal asymptotes. And remember, so this is as x gets large, what does y do? But as x gets large, in this problem, y goes to, and you pick the biggest power in the numerator, that term, and the biggest power in the denominator, that term, which is x squared. So this one's a little bit different than what we've been seeing. And so notice one of the x's cancels, and you're left with 1 over x. Now remember that x is getting to be a big number. So if x is getting to be a big number, I want you to think about what happens to 1 over x. You know, think about what happens as the denominator gets to be a bigger and bigger number in the expression 1 over x. So 1 over 10, 1 over 100, 1 over 1,000. Right? What's happening? That's getting closer and closer to 0. And so that's what's happening here. That's the y value is getting close to 0. And so that's our horizontal asymptote is y equals 0. In other words, the x-axis. And I want you to see that this is always what's going to happen when the degree of the numerator is smaller than the degree of the denominator. That you're always going to get a horizontal asymptote at y equals 0. So that will always be true when the degree of the numerator is smaller than the degree of the denominator. Then that's always going to be what happens, is that you get y equals 0 as a horizontal asymptote. All right, and then we have the x-intercept. And remember, the x-intercept is where the numerator is equal to 0. And the numerator is equal to 0 in this problem when x is equal to 1. And so that's our x-intercept at 1, 0. Now notice that 1, 0, you know, that's an x-intercept, but the x-axis is the horizontal asymptote. So this is a graph that actually crosses its horizontal asymptote. And then the y-intercept, we substitute 0 for x, and you get y equals 0 minus 1 over 0 minus 9, or positive 1/9. So you have a y-intercept here at 0, 1/9. All right, so let's see if we can figure out a general shape for this graph. This is a more complicated graph than what we've seen because it has two vertical asymptotes. That means that it's got to have 3 branches to the graph, right? There's a vertical asymptote here at -3, x equals -3. There's another vertical asymptote at x equals +3. So what I want you to see is that there's a branch in this area, right? To the left of that asymptote, there's a branch sitting in between the 2 asymptotes. And then there's a branch sitting over to the right of this last asymptote. Right, so there's 3 branches to this graph. All right, the horizontal asymptote is actually on the x-axis. I'm just going to put this dashed line just a little tiny bit off just so we can see it right there. There's an x-intercept at 1, 0. So there's an x-intercept here, and then there's a y-intercept at 0, 1/9, which is really small, and so that's kind of exaggerating it a little bit. All right, so since those asymptotes were in that inside branch, let's focus on that inside branch and where that might be located. And maybe let's plot another couple of points. So like x equals 1 might be a good value to pick, and x equals -2 might be a good value to pick. So let's look at f of 1 and f of, that's x equals 2, I'm sorry. Yeah, so that would be f of 2 right there. That's better. And f of -2. So f of 2 is 2 minus 1 over 4 minus 9, or 1 over -5. So f of 2 is -1/5. So it's a value down here. It's pretty small again, but it is negative. F of -2 would be -2 minus 1 over 4 minus 9, or -3 over -5, which is positive, and it's +3/5. So kind of exaggerated a little bit where it's located, but it's located right in here. And so those points start giving you the idea that there's a branch sitting in here that's kind of tucked in like this, and it gets really flat right in here, and then comes down like this. This is a common type of middle branch to have, is a graph that kind of vaguely reminds you of the cube graph flipped upside down. And that's our branch in between those 2 asymptotes. Now on the outside of the asymptotes, now look, on the outside, think about to the right here, there's only 2 places where this branch could really be. This branch is either going to sit above like this, or the branch is going to sit below like this. That's really all that can happen. And the same thing on the far left. You either have a branch up here or a branch down here. Now you can't, and so you just have to figure out which one you've got, right? And there's various ways to do that, but I'm just going to plot some points to do that. So like I might pick 5 on this side and -5 on this side to see where those branches are. So we're going to look at f of 5, which would be 5 minus 1 over 25 minus 9, or 4 over 16, or 1/4. So f of 5 is at 1/4. It's pretty small, but we're going to exaggerate where it is, but it's positive. And f of -5, you get -5 minus 1 over 25 minus 9, and you get -6 over 16, or -3/8. So -3/8 is like right about down here. It's negative. That's the important thing. And so that gives you a pretty good idea that this branch is going to be sitting above the horizontal asymptote like that, and this branch is going to be sitting below like this. Again, this would be a place to use your graphing calculator to help you with where those branches are, or even to plot a few more points if you wanted to try to figure out where those branches happen to be sitting. Plotting points is never going to hurt to do that. Using your graphing calculator is never going to hurt to try to find out where these branches are like that. Now, this takes some practice, and so using your graphing technology to your advantage, would be helpful, certainly. Let me give you some textbook problems to look at also, and emphasize that you should be working on WebAssign. But so textbook homework. This is on page 431 of your book, and these are problems numbers 11, 13, 15, 19, 21, 23, 39, 41, and 43. Now remember, we are not going to look at slant asymptotes, and I'm generally going to typically not have you find places, unless they're intercepts, places where the graph crosses its horizontal asymptote. So don't worry about slant asymptotes. Do not worry about slant asymptotes. Also, we didn't talk about this at all, really. Don't talk about don't worry about holes in graphs also. Now the hole in a graph, just briefly here to finish this up, we've talked about how to find vertical asymptotes, right? So the vertical asymptote, we talk about the denominator being equal to 0, but notice at x equals 3, what do you get? That the denominator is equal to 0. And so that means that there's a vertical asymptote at x equals 3. But notice at x equals -2, both the numerator and the denominator are both equal to 0. And in that case, you do not have a vertical asymptote, no vertical asymptote there. Instead, what you have is a hole, literally a hole in the graph at x equals -2. And let me refer you to the top here. We're not going to worry about holes in graphs. That'll be more of a pre-cal topic. So I'm just going to look at places where the denominator is equal to 0, not places where both the numerator and the denominator are equal to 0. Okay? So just kind of briefly mention that at the end. All right, so work on this homework. And so for those of you who are with me, you've been watching, anybody have anything that they want to mention or ask about before we shut it down? It's gone pretty quick here, for me at least, for this hour and 20 minutes or so. Anybody have any questions?
No questions here yet.
I'm good for now, thank you.
Okay, practice and watch the video. We will talk during the week. Don't forget my online office hours. Don't forget I'll be on campus the following week, not this week, but the following week. Everyone have a great week, and I will be in touch. Thank you.